Greetings and welcome to Physical Science at Hack. In this video we will go through some of the sample problems for Chapter 7 on light in our textbook. And we'll work through 5 different problems here and some similar ones to what you'll see in the homework and problem sets coming up. So let's start off with our first one here. Our first problem asks how many minutes are required for sunlight to reach Earth if the sun is 1.5 times 10 to the 8th kilometers from the Earth. Now, as we always do, let's start off with what we know. We know the distance is now 1.50 times 10 to the 8th kilometers. Is that everything we know? Actually, there's one other thing we know too that will be very useful in this problem, and that is the speed of light. The speed of light is 3 times 10 to the 8th meters per second. So, what do we need to do here? We have one difficulty we have is that we have 2 different units. We have the distance in kilometers and we have the speed of light in meters per second. We have to change one of those. So there are 2 different ways to do this. We can change the distance into meters, or we could change the speed of light into kilometers per second. Let's go ahead for this case. Let's change the distance into meters. So the distance is 1.5 times 10 to the 8th kilometers. And we know that there are 1,000 meters in 1 kilometer. So our kilometers will cancel, and our answer will be in meters. And the distance in meters is then 1.5 times 10 to the 11th meters. So you have to always watch your units and make sure that you're keeping things in the same sets. You can't just multiply or divide kilometers and meters. You have to make sure the units are the same. So now that we know that, let's see what we need to do. We know that the distance equals velocity times the time. And what we're looking for is the time. So time is equal to distance divided by velocity. Or in this case, the time is equal to the distance, which we now found is 1.5 times 10 to the 11th meters, divided by the velocity of 3.00 times 10 to the 8th meters per second. Well, if we divide those 2, we will get meters cancel, seconds come up on top, and that will give us 500 seconds. Now, only thing is we want our answer in minutes. So we have to do another conversion here and say that 1 minute is 60 seconds. And when we divide those, we find out that it would be 8.33 minutes would be the time that it takes the light to traverse the distance between the Earth and the Sun, traveling at the speed of light. So it takes the sunlight we see now when you go outside is actually sunlight that left the sun over 8 minutes before. Now for our second problem, says the wavelength of a monochromatic light source is measured to be 6 times 10 to the negative 7th meters. And we want to know what the frequency of that light is and what the energy of a photon of that light is. So let's write down what we know. We know that the wavelength of this light is equal to 6.00 times 10 to the negative 7th meters. Now, that's the only thing we're given in the problem, but remember we do know some other numbers, and we're probably going to need things like the speed of light, which is 3 times 10 to the 8th meters per second, as we used in the previous. We also are going to need Planck's constant, which is h, which was given to be 6.63 times 10 to the negative 34th, and that's joule seconds, the units for that, joule times seconds. So we're going to need each of those when we do this problem. So now that we have those, let's do our first section here. First of all, we want to find the frequency. We know that the speed of light is equal to the wavelength times the frequency, or frequency equals the speed of light divided by the wavelength. So we know the speed of light, we know the wavelength, we can now calculate the frequency. So frequency is equal to 3.00 times 10 to the 8th meters per second divided by the frequency, the wavelength that we have, which was 6.00 times 10 to the negative 7th meters. And if we divide those two, we then find that that is equal to 5.00 times 10 to the 14th. Meters have canceled. Units are 1/second. And if we recall, 1/second means a hertz. So 5.00 times 10 to the 14th hertz. So that's frequency. That's what we're looking at for the first one, first part of this problem. For the second part, we want to find the energy. Now, if we remember, Planck's equation said that energy equals h times the frequency. Now, we've just found the frequency. We can now use this to find the energy, which is equal to 6.63 times 10 to the negative 34th joule seconds times the frequency that we just determined, 5.00 times 10 to the 14th hertz. And when we multiply those two, we would then get the energy being, remember that hertz is 1/seconds. So seconds times 1/seconds, that will cancel. And all that will be left is an energy in joules. And in this case, when we multiply those, we will find that it is equal to 3.32 times 10 to the negative 19th joules. So then we find our answer for the energy of that photon as well. Now for number 3, let's look at our third problem here. And we're going to look at what the energy is of a gamma ray photon of frequency 5 times 10 to the 20th hertz. So again, we know the frequency in this case. Frequency is 5.00 times 10 to the 20th hertz. And do we know anything else? Well, we're going to need one other thing, and that is Planck's constant that we used before, 6.63 times 10 to the negative 34th joule seconds. So now that we know those, let's go ahead and figure this out. We're going to use the same equation we did last time. Energy equals h times frequency. And we know that h is 6.63 times 10 to the negative 34th joule seconds times the frequency of 5.00 times 10 to the 20th hertz. And if we multiply those, again, we have to remember, get rid of the hertz here, that's 1/seconds, and those cancel, leaving us just with joules. And that gives us 3.32 here, 3.32 times 10 to the negative 13th joules. So there is our answer for the third part, for number 3. So let's move on. We've got a couple like these. We're going to do one more similar one, which says that what is the energy of a photon of orange light now with a frequency of 5 times 10 to the 14th hertz. So we know what the frequency is, again, and we're going to find, let's put our numbers down that we know. Frequency this time is 5.00 times 10 to the 14th hertz. And of course we need to know Planck's constant to do this, which is 6.63 times 10 to the negative 34th joule seconds. So you should be getting quite good at this type by now. What do we know? What's our equation? Energy is equal to h times the frequency, which is 6.63 times 10 to the negative 39th joule seconds times 5.00 times 10 to the 14th hertz. And that gives us, when we multiply those, 3.32 times 10 to the negative 14th. Once again, that's 1 over seconds to cancel the seconds and joules, and that gives us our final answer for this case. Now, something a little different for our last problem. What our last problem says is that at a particular location in time, sunlight is measured on a 1 square meter solar collector with an intensity of 1,000 watts. If the peak intensity of the sunlight has a wavelength of 5.6 times 10 to the negative 7th meters, how many photons are arriving each second? So a little bit tougher here. Let's see what we know. We know the wavelength is equal to 5.60 times 10 to the negative 7th meters. We know, of course, we know H and C. We're going to need these. H is 6.63 times 10 to the negative 34th joule seconds. We know that C is equal to 3 times 10 to the 8th meters per second. And we know the intensity is equal to 1,000 watts. So what do we need to do first? We know the wavelength. First we need to find the frequency, because we're going to need to find the energy of these particles. We want to know how many photons we have to find. First we're going to find the frequency. So let's find the frequency. Frequency, we've done this before, is equal to the speed of light divided by the wavelength, which is equal to 3 times 10 to the 8th meters per second divided by the wavelength of 5.6 times 10 to the negative 7th meters. Our meters cancel, leaves us with 1 over seconds, which is hertz, or a frequency of 5.36 times 10 to the 14th hertz. Okay, so our next step is we want to find the energy. We've done this a couple times already. Energy is equal to Planck's constant times the frequency, which is equal to 6.63 times 10 to the negative 34th joule seconds times the frequency that we just got up above, 5.36 times 10 to the 14th hertz. So if we multiply those together, and again we've done this several times, the seconds there cancel, leaving us with just joules, and it gives us 3.55 times 10 to the negative 19th joules. Now, the next thing that we want to find is we're trying to find the number of photons. We know what the intensity is. The total intensity of all of these photons hitting at once is 1,000 watts. And if you recall, 1,000 watts is equal to 1,000 joules per second. Now we know how many joules each photon has, and we know how many total, so now we can figure out how many photons are striking each second. And we can find that by taking the 1,000 joules per second, or watts, and divide that by the number of joules per photon that we just determined, 3.55 times 10 to the minus 19th joules per photon. Well, that's equal to, let's see what we get here. We will divide those two and we will get 2.82 times 10 to the 21st. Now what do we get for units? We have joules per second, and then from the denominator we have photons per joule. Recall, when we bring this up to the top, it flips over. So the joules cancel, and we end up with 2.82 times 10 to the 21st photons now per second for our answer. So that concludes our working of the sample problems for Chapter 7 on light, and we will continue on with Chapter 8 next time. So until then, have a great day, everyone, and I will see you in class.